Okay, so here, the next thing to do is to figure out what states, how to step this thing through. We had all those flip-flops doing kerchunk, kerchunk, so we have to figure out, okay, what do we actually want them to do each step? Now, one thing we're constrained by is the Raspberry Pi GPIO, how many GPIO pins it has. It does not have enough pins to have separate address and data. So you have to have one cycle to put address in it, and then another cycle to take the data out of it if you're reading, or one cycle to put address in it, and then the next cycle to put the data in it if you're writing. So we have to take that into account when we figure out what states we're going to use. Okay, but other than that, we're pretty much on our own to figure out what we need to do. So we know a PDP-8 design likes to use like fetch, defer, and execute, right, for its major states. But we need to figure out, okay, what do each of those states, what are they actually going to do? So we have like the fetch state. Okay, what that does is that reads memory location given by the program counter. Okay, so we know from the way the Raspberry Pi is set up that it's going to take us 2 clock cycles, one to send the program counter to the Raspberry Pi and the other to read the opcode back. So what I do is I have a fetch 1 and fetch 2 cycles. So I'll draw those as circles here. Fetch 1, and then next to it fetch 2. Now these circles here just represent a state, but the way this is implemented now, there's actually a D flip-flop called fetch 1, and there's a D flip-flop called fetch 2. Okay, and the Q output, actually goes to an LED on the front panel that says, "Oh, this flip-flop is on." And for each of the various states here, we're going to do the other states here eventually. But there's a LED that lights up when each one of these state flip-flop is on. So it'll tell you which state it is. And only one of these should be lit up at a time. There should be exactly one of these at any time the processor is running. There should be exactly one of these flip-flops lit up, with the corresponding LED lit up. So now we're going to determine, okay, when it goes from each one of these states and when each one of them is needed. So now there's a reset signal, okay, and that sort of starts it off. If you put the reset signal on, no matter what it was doing before, it's going to turn the fetch 1 flip-flop on and turn all the other state flip-flops off. So applying the reset signal is just going to stick it in fetch 1 no matter what it was doing before. Okay, and then you release the reset signal, and then you wait a little bit of time so it soaks into the tubes really good, and then you can kerchunk it, and that will have it go on to the next state. So we're going to write here fetch 1, and what does that do? That sends the PC. We don't know how yet. We're just going to say send PC to Raspberry Pi. Okay, so that sends the program counter to the Raspberry Pi in fetch 1. Okay, now it always, if you're in fetch 1, you get a clock kerchunk. We'll just draw an arrow there, always. So we're not going to write any conditions on there because it always goes from fetch 1 to fetch 2 when you get the kerchunk. And fetch 2 is going to load the IR from the Raspberry Pi. Okay, so when we send the program counter to the Raspberry Pi, and we can also tell it to read memory. Okay, so we're going to send the program counter to the Raspberry Pi and tell it to read memory. And then the Raspberry Pi on the next cycle, the Raspberry Pi is going to see these signals just before it kerchunks the clock up, right? It's going to read its GPIO pins and see, oh, I'm getting a read memory thing, and it's going to say, okay, well, the address is going to be on the 12 address data pins, right? And it will see that program counter there, and it will know to read the memory location, and then the next clock cycle, the Raspberry Pi is going to respond by putting the data from that memory location out on those data pins. And then when this thing chunks into fetch 2, the little combinational logic that's connected up to the output of those all these flip-flops is going to cause the instruction register to accept data from the Raspberry Pi and load it into the instruction register. Okay, so the fetch 2 is going to load the instruction register from the Raspberry Pi. Now another thing fetch 2 cycle is going to do is it's going to increment the program counter. Increment program counter. Okay, so that's sort of a separate thing. So it's doing two separate things here. It's going to increment the program counter. Okay, so that's sort of what the fetch 2 instruction does. Okay, or the fetch 2 state does. It's going to load the instruction register from the data it gets back from the Raspberry Pi and increment the program counter. Okay, now the next thing to do a PDP-8 instruction is there's defer cycle, right? So if there's an indirect memory instruction like, oh, I don't know, deposit DCA indirect, some memory location, is it has to read the pointer out of memory, right, to figure out what address the operand goes in. So it might do a defer next, we don't know, depends on what the opcode is. It might go to defer, so we'll just write defer here. Maybe we'll have to do defer next. Or it might just be able to go execute the instruction right away. Like if it's a TAD instruction that has just the address of the operand directly in the instruction itself, it might jump over and do the execute cycles. But we'll do those in another minute. So we're going to write on here, only if indirect memory instruction. Okay, only if indirect memory instruction is it going to go to defer. Okay, all the others we haven't drawn yet. So this will be implemented as a gate, right? There's going to be a D flip-flop that's going to have a D input that will be a gate, and that gate will say if it's in fetch 2 and we're getting an indirect memory instruction from the Raspberry Pi, then it will go to defer 2. So this is going to be a little gate. Okay, and if you look in that seq.mod modules file, there should be something in there that says defer 1D for the data input to the defer equals, and then some little Boolean equation. That's going to look something like that. But anyway, for this purpose of the state diagram here, we can just write, okay, only if indirect memory instruction do we go to defer. Now, how many cycles can defer? How many cycles do we need for defer? Okay, now, usually this is just reading memory. So we just read the pointer. We have to send the address of the pointer to the Raspberry Pi in one cycle, and then we read the pointer value back in the second cycle. But there are also auto increment pointer locations, right? Pointer addresses 0010 through 0017, right? Are auto increment. They have to be incremented. So that's a read, modify, write cycle. And that takes 3 clock cycles, right? Because the first one is you send the address of the pointer to the Raspberry Pi. The second cycle is you get the value back that was in the pointer value, and then you have to increment it and send it back to the Raspberry Pi, right? Because we want to have the Raspberry Pi just have the only smarts, that only a stupid memory controller, so that theoretically the Raspberry Pi could be just a dumb memory controller. We want the processor to do all the thinking part. And the Raspberry Pi is just a stupid memory controller as far as the processor is concerned. Okay, so we could possibly need 3 defer cycles. So we're going to have defer 1, defer 2, and defer 3. We might need defer 3. I don't know if we're going to need it yet or not. We'll have to figure that out. When are we going to need defer 3? Because it might possibly be a read, modify, write. Okay, so that takes up to 3 cycles. Defer 3, 1, 2, and 3. All right, so this defer 1 is going to be very similar to fetch 1, except we're going to send the pointer address to the Raspberry Pi and tell it to read. Tell it to read. Now, the way the Raspberry Pi program works, if we want it to do a read, modify, write, we have to tell it now. So, and maybe also write. Okay, so that maybe is if it's if the pointer address is anywhere from the 0010 to 0017, we'll also set this bit to tell the Raspberry Pi, okay, it's a read and then it's a write as well. Okay, so then the Raspberry Pi is going to see this, and then it's going to kerchunk the processor over to the next state. And the next state after defer 1 is always defer 2, okay, to read that pointer value back. So we're going to get the pointer value back, get pointer back from Raspberry Pi. And actually put it in the memory address register, to memory address register. You see a memory address on the front panel of the Raspberry Pi, or on the front panel of the tube computer, and that's the memory address register. So this is one instance that the memory address register gets loaded from the Raspberry Pi here. Okay, so now what is the next state? That's pretty simple. It just takes the value it gets from out the data bus from the Raspberry Pi and kerchunks it into the memory address register, right? Okay, now what is it going to do next? Okay, it's either ready to do the instruction right now, because if it's not auto increment, it's ready to go, right? We know the address of the operand. But if it was an auto increment instruction, it has to do this defer 3, and also the Raspberry Pi is waiting for this modified value back. So what it will do is it's auto increment. So we'll write this here, auto increment only. Okay, so only if it's an auto increment instruction is it going to do defer 3. And what do we do here? Okay, we're going to add 1 to the MA, and send it back, send to Raspberry Pi. Okay, so it's going to add 1 to that memory address register only if it was an auto increment. Okay, and now we have in the memory address register, coincidentally, we have the incremented value, and also the Raspberry Pi is going to store it back in memory, that incremented value. So if we go use that pointer again, it will be incremented for us to work. Okay, so now the next big thing here is execute cycle. So we'll shuffle this over here. Now we're actually ready to execute an instruction. Okay, so let's say here not auto increment, not auto inc, and this would be always, right? because only always. Okay, so and then this here from the fetch too. I guess we weren't quite ready to shuffle, were we? Everything else is going to come over here like this, and this indirect. It only did this with indirect memory instructions. So this is um, direct memory, or one of the IoTs, or one of those group one, group two, whatever instructions, right? Those are going to come over here. Those don't need any, those don't have any memory operands or anything. So those will all go over to exec 1. So we'll say, okay, we don't know how many execute states we need yet, but let's say we know we need at least one, so we have exec 1. Okay, so how many execute cycles are we going to need? Okay, some instructions just read memory, so you have like and tad, those just read memory, so we know we need at least 2. And DCA just writes memory, and that only takes 2 cycles. You have to one cycle to send the address to the Raspberry Pi, second cycle to send the data to the Raspberry Pi. Okay, so that takes 2 cycles. There's increment and skip if 0. Now that's a read, modify, write. You have to send the address to the Raspberry Pi, tell it to read and write memory. Then you read the value back from the Raspberry Pi. Then you increment it and send it back to the Raspberry Pi to write memory, to write the updated value back to the memory. So that takes 3 cycles. Okay. Um, the input output instructions. Okay. You need a cycle to send the accumulator to the Raspberry Pi, the existing accumulator, and then read the updated accumulator back from the Raspberry Pi, because it pretends, as far as the processor is concerned or the tubes are concerned, the Raspberry Pi is also just a bunch of dumb I/O devices like, a teletype interface. And all it does is it's able to send the accumulator to the I/O device and then read back on the next cycle the updated accumulator and possibly a signal saying, okay, do a skip, right? Because those things have to skip. Or I/O instructions can tell the tubes to skip the next instruction. Okay, so that takes 2 cycles. So the longest one we have so far is 3. And as far as the group instructions, like clear accumulator, shift, rotate, all those sorts of things, that should all be doable in one cycle because it isn't doing any memory accesses. So it's just updating the accumulator on its own. So we should be able to do that in one cycle. So it boils down to then that we need 3 execute cycles, okay? Because that's the longest one, that, like the increment and skip if 0, is the longest instruction. So we take 3 executes. We'll draw those out here like this. Exec 1, exec 2, and exec 3. Okay. Now, one way to think of these, this is how they're actually organized in the actual hardware, is there's 3 flip-flops here. But another way to think of this is there's 3 states, up to 3 states for each of the different kinds of instructions. So we can really sort of forget about this for now and break it down into, okay, so we have like the AND instruction. Okay, so that's the first instruction we have is AND. And how many states does that take? AND. Okay, again, that's reading memory and updating the accumulator. So we can send the address of the operand to the Raspberry Pi in the first cycle and read the operand back and update the accumulator in the second cycle. So AND should only take 2 cycles if we do this right. So this comes in here from, either from fetch or, defer 2 or defer 3, could be any one of those. could come into AND 1 if it's an AND instruction, okay? And this tells the Raspberry Pi to read memory. And the address is in the MA register, okay? So it will read that, send the memory address register off to the Raspberry Pi, and then this cycle here will get the operand from Raspberry Pi and AND it into the accumulator and into the accumulator. So what it's going to do is it will take the value it gets back from the Raspberry Pi and shove it through the ALU, and that will perform the AND operation. And then by the end of the cycle, it should be ready to get kerchunked into the accumulator and update the accumulator. So, and this is an always, okay? So when it gets into AND 1, it's always going to do AND 2. So this arrow is just unconditional. It always goes to AND 2, okay? And we're going to talk about, this is the last cycle of an instruction, and we'll talk about what it does later on. Okay, what it does next, how it figures out. Basically, it goes one or two places. It either goes to fetch 1 if there's no interrupt request, or it goes to that interrupt acknowledge cycle if there is an interrupt request. But we'll talk about that later. Okay, so TAD is very similar. Okay, TAD, there's TAD 1, TAD 2. Okay, and it does this very similar thing. However, for doing an add in the ALU is slow, okay, because you have the carries. Even with the carry look-aheads, it's slow. So we actually put a TAD 3 cycle in here. And that gives it extra time to do that addition in the ALU. Okay, ANDing is very fast, that's just what, 2 gate delays or something like that. Whereas doing an addition, I don't know, it's probably might even be like a dozen gate delays or something like that. So TAD 1 goes to TAD 2 and then goes to TAD 3. Okay, so again, this is reading, tell Raspberry Pi to read memory with the memory address register. And then this gets the operand, and it just sticks it in the memory address register. Put in, it's not really a memory address, it's a memory value, but well, just call it the MA. And then here we add MA to the accumulator and a link, so we can say and link, right? So this gives it a whole cycle. It's already got the value from the Raspberry Pi in the memory address register, so when this thing kerchunks in here, those values, it doesn't have to wait for it to come from the Raspberry Pi. It's got it immediately, and it can start doing the addition right away here. So that lets it go a little faster, or gives it time to get all the way through the ALU addition circuit. If we had tried to do it all in here, you would have to make this cycle very long, right? So because the time to get it from the Raspberry Pi and then work its way through the add circuit, it would make these cycles long to read things from the Raspberry Pi. Whereas if we put it over here in its own cycle, it can have time to work through the adder circuit. Okay, so that's why this is done this way. Now, one thing about TAD, again, it can come from any one of these 3 here, right, if it's a TAD instruction. Now, one thing about the TAD instruction is it is used a lot when the accumulator is 0 as a load, just to load a value into the accumulator, okay, the TAD instruction, and it takes 3 cycles, that's kind of silly to take 3 cycles. If you know the accumulator is 0, there isn't going to be any carries or anything no matter what you try to add, right? So there aren't going to be any carries at all. Okay, if you're just adding and you know the accumulator is 0 to start. Okay, so what this processor will do to save time for the common case of doing a TAD that follows a DCA, or anytime the accumulator is 0 and you do a TAD, is it pretends it's an AND instruction and the accumulator is all ones. Okay, so it will do these 2 cycles here for an AND instruction, just as a little optimization to speed it up a little bit, right? Because if you know the accumulator is 0, you know it's not going to take any time to do any carries. Okay, so we're not going to need to waste time doing this. And doing a TAD to an accumulator of 0 is exactly the same as doing an AND if the accumulator is all ones. So it'll actually go and do these AND steps, okay, if the accumulator is 0, and just pretend the accumulator had all ones in it. Okay, well, that's just a little thing, but mostly TAD instruction in general takes 3 cycles, and you have 1 cycle here that's just doing nothing but the letting it soak through the ALU to do a full add, to update the accumulator and link. Okay, so that's the AND instruction, the TAD instruction. DCA is 2 states, right? Because you have to have one to send the address to the Raspberry Pi. So send address, MA to Raspberry and tell it to write. And tell to write. And this one sends the accumulator to the Raspberry Pi. Okay, and then it also clears the accumulator at end of cycle. Actually, it loads, it puts, all the data pins going to the accumulator, it puts zeros on all of those, and then when the clock cycle comes along at the end of the clock cycle, it kerchunks in a 0. Okay, so DCA1 goes to DCA2 like that. Okay, so that's pretty simple. And just so I don't bore you silly, all the other instructions are very similar. Okay, ISZ, tell this, that time it's going to tell the Raspberry Pi to, here's the address, I'm going to read, then write. Okay, and then ISZ2 gets the value from the Raspberry Pi, increments it, and sends it back on the 3rd clock cycle. Okay, so that's how ISZ works. And what do you got? GMS and jump and all those guys. Okay, jump just takes the memory address register and writes it to the program counter. Okay, so so it's not really interacting with the Raspberry Pi at all. It's already got the address in the memory address register. It just writes it to the program counter. That's how jump works. JMS writes the old program counter. JMS takes 3 cycles. The first one is writing, the first 2 of them are writing the old program counter to memory. So that's a write operation that takes 2 clock cycles. And then the 3rd one is plunking the memory address register, incrementing the memory address register and plunking it into the program counter. So that's how JMS works. IoT, very similar. It sends the accumulator and link to the Raspberry Pi on 1 cycle, and then reads the updated accumulator and link on the 2nd clock cycle. And the group instructions, they just do, fill with the ALU to tell it to do, the rotates and the increments and the complements and all of that stuff. And that just happens in 1 clock cycle. But this is the the main thing here. Okay, once you have these states here, I guess I can fit most of it in the camera. I'll get it all in the camera. So this is the main thing. You know, you have fetch 1, fetch 2, the defers, and then these cycles here. Okay, now there aren't separate flip-flops for all of these. Okay, this is really the exec 1 flip-flop. Okay, all of these various such and such 1, such and such 1, such and such 1. This is really a flip-flop exec 1. And same here. This is really all exec 2. And this is all exec 3. You know, like there's an ISZ in here, right? I said ISZ, so that would be in there. So this is really all just a flip-flop called exec 1. Exec 2. Exec 3. Okay. And then on combinational logic on the output of exec 1 flip-flop is going to say, okay, well, it was an AND instruction, so we're going to tell the Raspberry Pi to read memory, or if it was a TAD instruction, we tell it to read. If it was a DCA instruction, we're going to tell the Raspberry Pi to write. Okay, but that's all part of exec 1, and similar with exec 2 and exec 3. I know it's a little complicated, but the idea is, okay, you could have separate flip-flops for each of these states, but then you would have a lot of flip-flops, and they're kind of expensive, right? Flip-flops are 3 tubes, right? 6 gates or 3 tubes, and that would make a lot of tubes. So it's easier just to use one flip-flop for each of these 3 states, and then have some decoding with a couple of gates on the output saying, okay, we're going to generate what control signals to the Raspberry Pi for exec 1, what control signals for exec 2, and what control signals for exec 3. Okay, so that's how it works. To use just 3 flip-flops, it saves a lot of gates. Okay, now assuming that it's finished, whichever is AND2 or TAD3 or DCA2 or whatever, now it's got to go back to process the next instruction. Okay, so it's going to check the interrupt request line. Okay, so the Raspberry Pi, right, it simulates all the I/O devices, and it pretends it's the disk controller and terminal controller and all that stuff, and so it has an interrupt request line coming out of it, just like you would expect on any I/O bus. Okay, so it has an interrupt request line. So if there's an interrupt request, let's say no interrupt request, no IRQ, then it's just going to go back around to fetch 1. Okay, if there's no interrupt request. If there is an interrupt request, then it's going to go to this state int ac1, int ac1. Okay. And what does a PDP-8 do when it gets an interrupt? It just does a JMS indirect memory location 0, and it also tells the or it also blocks further interrupt requests. Okay, so int ac1, it's going to tell the Raspberry Pi to stop sending interrupt requests. Stop interrupt request. Okay, so that's one thing it does. Now it's also going to do the same thing as a JMS 0, right? So what does JMS 0 do? Well, it tells Raspberry Pi, it's also going to tell Raspberry Pi that we want to write memory location 0. Going to write memory location 0. So it sends an address of 0 to the Raspberry Pi, tells the Raspberry Pi, okay, we're going to write memory, and it also tells the Raspberry Pi stop requesting interrupts. Okay, because you can't keep requesting interrupts every cycle or you'd never get out of there. Okay, and now since the Raspberry Pi is doing does the exact same thing as a JMS 0 instruction. Okay, it also sticks JMS 0 into the instruction register. Okay, so that's what it's going to do. It does these three things. Okay, it tells the Raspberry Pi stop requesting interrupts. It tells the Raspberry Pi we're going to write memory location 0, and it also sticks a JMS 0 instruction into the instruction register. Okay, and then it can just go on to do JMS 2, a JMS 2 cycle, which sends the program counter to the Raspberry Pi. Okay, just a regular JMS as if it were a JMS instruction, because we have a JMS 0 instruction in the instruction register. So we can just let it go ahead and do what a JMS instruction would normally do. And then JMS 3 here, right down here in the corner, JMS 3 puts the address, address plus 1 into the program counter, right? So that's what a JMS instruction does, right? We put a JMS 0 in there, so it'll end up with a 1 in the program counter, which is how a PDP-8 interrupt request works, okay? And then JMS 3 will then go on to fetch 1 because we've turned interrupt requests off. Hopefully this interrupt request line will be shut off by the Raspberry Pi, and so it will go on and go back over here, fetch the first instruction of the interrupt subroutine because the program counter now has a 1 in it. So that's how the interrupt works. Okay, so it has its own little state to get things going here. That's either triggered at the end of instruction if there's an interrupt request by telling the Raspberry Pi to stop requesting interrupts, and then store the program, or tell it we're going to write memory location 0, and sticks a JMS instruction in the instruction register. I think it's opcode 4000. So if you stop the tubes at this point, you should see a 4 on the panels in the instruction register, because 4 is the opcode for JMS. And then the second cycle of a JMS instruction sends the program counter to the Raspberry Pi, so it writes it to write to memory, to write to memory 0, location 0, because we gave it memory location 0 here. Gave it the address of 0 here, and now it knows to write. The Raspberry Pi knows, okay, whatever data it gets, it writes it to that memory location. And then the third cycle increments the program counter. Okay, so that's how that works. That's how interrupt works. Now there's another little optimization here that this thing does. Okay, so let's do the jump instruction. Okay, we didn't do that on the other page. We'll do it now. Jump 1. Okay, now all the jump instruction has to do is take whatever's in the memory address register and put in the program counter. Okay, that's all it has to do, right? And then it could go on, and let's assume no interrupt request. It could go on to fetch, but go back, loop back around to fetch 1, which sends the program counter to the Raspberry Pi to read the next instruction, right? What you jumped to. Okay, but what we can do is, see, this jump cycle isn't doing anything with the Raspberry Pi, and we have the address of the next instruction here already, so we can simply tell Raspberry Pi, hey Raspberry Pi, start reading that location. Start reading. Read. Okay, because remember how the Raspberry Pi memory read goes. You take one cycle to send the address you want to it, and then the next cycle you read the data back. So we can start read from MA, from whatever's in the memory address register, right? Just like it was a AND instruction, and you know, you're going to read the operand value that you want to AND, um, you're telling the Raspberry Pi to read that. Well, here you're telling the Raspberry Pi, start reading this thing here. And then instead of going to fetch 1, you can go to fetch 2. And that saves a memory cycle, or that saves a clock cycle, right? Because fetch 2 says, okay, take that value from Raspberry Pi, and put in instruction register. Put in instruction register, IR. Okay, that's what fetch 2 cycle does. If you look back here on this fetch 2 page, load instruction from Raspberry Pi and increment the program counter. And we still want to increment the program counter. Increment PC just as it always did before. So this is the same exact fetch 2. Okay, we just kept the Raspberry Pi busy this cycle, and so we could shorten it. So we've combined the fetch 1 cycle with the jump 1 cycle. Okay, so that saves a clock cycle for jump. So effectively, jump has no execute cycles because it's overlapped the next fetch with its execution. Okay, and you can do the same with the JMS3 cycle. JMS3, right? It's in essence doing the same thing. It's putting the memory address register plus 1. That's all right, MA plus 1. So it's incremented the MA register plus 1, sticks that in the program counter. And then it tells the Raspberry Pi to start reading from MA plus 1. Okay, and then same thing, fetch 2. And that just saves a memory cycle, right? Or that just saves a clock cycle. That's all that's doing there. Fetch 2, okay? And there's one other place it can do this, okay? There are those the skip instructions, okay? Skip, right? Skip if like accumulator less than 0 or whatever. The various conditions are skip if AC equals 0, etc., etc., okay? That's exec 1 type state, a group. I think I call it group. I call it group B1, okay? And but it's really the exec 1 flip-flop. And that again can tell the Raspberry Pi to read from either PC or PC plus 1. Okay, so that's again an optimization it can make so that it doesn't have to waste this cycle, and fetch 2 comes next. Okay, because in the next cycle the Raspberry Pi is going to say, okay, here's your opcode. Okay, this thing has to decide, by the end of this cycle whether or not it's skipping or not, and increment the program counter by 1 or not. And then fetch 2 is going to come back with the opcode that you read from either PC or PC plus 1. Okay, so these are just optimizations, okay, that it can do to save a clock cycle. Because the idea is you want to keep the Raspberry Pi, you want something going into the Raspberry Pi every clock cycle if you possibly can, okay? So the only 2 cycles that aren't interacting with the Raspberry Pi is this tab 3 cycle, because it's going to give a full cycle for the accumulator to do its addition, or the ALU to do its addition, right? And the other one is group 1 instructions don't have any optimization because they're busy using the ALU to actually complement the accumulator and rotate it and do all that craziness. So it can't be doing a program counter operation here or any of this other stuff. So it's busy. The ALU is busy. So the group 1 instructions won't overlap. Okay. But all these others can overlap and they keep the Raspberry Pi busy every cycle. All right. Now another note here is if you like set a jump instruction to jump to itself, okay, you would say, oh, well, it'll never recognize an interrupt. If you did, jump to self, right, that would go fetch 1. Let me get the sheet here for fetch 1. That would do fetch 1 to get the jump dot, fetch 2 to get it into the instruction register, and then would do jump 1 to put the program counter back to the same jump instruction and read the same jump, and then it would go to fetch 2, okay, immediately, and just keep doing. The fetch 2 would go back to the jump 1, and then it would never get out of here even if there was an interrupt request. Okay, so the processor is smart enough to know, oh, if there's an interrupt request, don't do any of this. Okay, don't do this if there's a interrupt request. Don't do this if there's an interrupt request. Don't do this if there's an interrupt request. Okay, it's still going to increment the program counter here by 1, but it's just not going to tell the Raspberry Pi to read, and then it knows to go to int ACK1 instead of going to fetch 2 after these. So if there's an interrupt request, it doesn't do this optimization. Otherwise, you could end up, like I said, with jump to self, um, uh, getting stuck, and the processor would basically be hung at that point. If you did a jump to self, it would never recognize an interrupt request or anything like that. So you have to not do this optimization if an interrupt request is pending. Okay. So anyway, I think that's all the details of all of that stuff, how these states work. So we covered fetching an instruction and doing a defer, right? Oh, this here also loads MA load into MA, load into MA. Okay, so it's going to load assuming that it was a direct operand address, it's going to load that operand address into the memory address register. Okay, so it also loads address into MA. I should have mentioned that earlier. So when it reads the instruction back from the Raspberry Pi, it goes into the instruction register, and also the corresponding address goes into the memory address register as well. So that when you go, like if it was a direct AND instruction or something like that, it has the address already in the memory address register ready to go. And or if it goes, to defer 1, well, the pointer address then is in the memory address register ready to go to the Raspberry Pi. All right, so there's those states: fetch 1, defer, and then again, some of the instructions here shown here, and then what happens in the last cycle of an instruction. It either goes to fetch 1 back here to get the next instruction, or it'll do the interrupt acknowledge sequence here, which is really just a JMS 0 instruction. All right, so those are the states, and each one of these states is a D flip-flop. And next video we can show, okay, now that we know what our D flip-flops are, what do the gates look like that go on each one of these flip-flops? Okay, this exec 1, exec 2, exec 3. These are a little messy, of course, but they're not too difficult to figure out. All right, so there's the state machine, and again, the state machine tells it what it should be doing each cycle. Okay, it sort of reconfigures the various other registers, the gating between all the other registers, depending on what state it's in and what's in the instruction register is are the big things. Okay, so there's that. Again, hope that was entertaining for you.